In our last video this week, I want to talk a little bit about spatial smoothing. So this isn't really part of the image registration process. This is the final pre-processing step that we almost always include before we analyze our data, but it's fairly straightforward, so we just go through it quickly. The idea behind spatial smoothing is that we want to account for the fact that there are these residual differences in size and shape across brains, and we don't normally care like to the millimeter where an activation is. What we care about is that it's in the same sort of anatomical structure and that that's consistent. And one way of dealing with that problem is to remove some of the high frequency spatial variations by smoothing the data a little bit. So any activation that you get might be very, very focal in a person. And if it's, at this point in one person and at slightly this point in another, then maybe they don't overlap naturally. But if you smooth them, then the two distributions are going to overlap more and you'll be able to detect commonalities better. We do it to increase the signal to noise ratio in our data. And it improves inter-subject averaging. A consequence of this is that it conditions our data. I mean, we are by definition changing the data, and therefore it's going to affect the way we have to do our statistics. But sometimes you'll hear people say that the reason that we do smoothing is so that we can make a particular type of statistical inference technique using Gaussian random fields work. We're going to talk about statistical inference and Gaussian random fields in some detail, but we do not smooth our data to make the inference work. We smooth our data because we're improving the signal to noise and we're improving the inter-subject averaging. A consequence of that is it's going to allow us to use a particular type of inference method based on Gaussian random fields. But if we weren't smoothing, we just simply wouldn't use Gaussian random fields. So it's incorrect to assume a causality there. It's the other way. We're smoothing because that's the right thing to do, and then we're going to apply stats that fit the data that we actually have. We are not adjusting our data to fit a cool stat technique. And the way we normally do this is using what's called a Gaussian filter. So you've all seen a normal distribution curve, right? This is a normal distribution in 2 dimensions. So there's a sort of this kind of Mexican sombrero hat shape. And if you rotate that in, say, 1 dimension, then you get a shape that looks like this. And that's a normal distribution or a Gaussian curve that can be described in different ways. For whatever reason, in imaging, we tend to describe these by measuring their full width at half maximum, right? So that is to say, if you measure the maximum height and go halfway down it, what's the width of the curve at that point? That's the full width at half maximum. But there's a one-to-one transformation between that and standard deviation. So if you prefer standard deviations as a measure of a Gaussian curve, then you can convert between them. However, all of the software, all of the papers will report everything in terms of full width half maximum. So it's a little bit counterintuitive if you grew up using standard deviation instead. But they're equivalent to one another. They're not the same, but you can map between them. And the key is that we're going to apply this smoothing kernel to our data in order to smooth it and make it, increase the signal to noise and decrease the variability, the anatomical variability between participants. So this is like looking at a 2D smoothing kernel as if you were above it. So that sort of Mexican hat shape thing, that is to say that, the effect that you're interested in when you're applying the kernel is based on a weighted average of the things near it. The things that are at the voxel of interest are weighted the best. The things that are around it, sort of the next door neighbors, have the next highest level of effect. And then the catty corner is even a little bit smaller than that. And it just fades off. So that there's only a certain amount of information in your local neighborhood that affects what your value is when you apply a smoothing kernel. And it's a very simple, straightforward calculation. It's a weighted average based on how far away from the current position you are. And to just illustrate this, what I've done here is I've created a plot that's got 128 values on the y-axis, 128 on the x-axis, and I just simply picked a random number for each of them and colored it according to high to low, right? So what's on the left is a pure random set of numbers with a lot of random numbers there, about 64,000. If I then smooth this using a Gaussian kernel, what you can see is the result on the right. So it's still random, but it now has a lot more sort of smooth structure because there's some areas that by chance show brighter effects and some areas that are darker than others, and there's more smooth transitions between them. But that's the effect of smoothing, right? We're just going to get rid of some of these high frequency variability in space, and we're gonna smooth them out by applying this Gaussian filter. One of the questions that comes up all the time is how much smoothing do you apply? What's the right amount? And again, there is an optimum answer to this, but it's not very helpful. So there's this theorem called the match filter theorem that says that the size of your smoothing kernel should match the size of your activation. And that's great, but if you knew the size of the activation before you did the study, you wouldn't really need to run the study. So we often don't have that information. Moreover, it's not to say that the activations in every part of the brain would be the same size. So if you have a small activation in, say, a thalamic nucleus, but a much larger activation in part of the prefrontal cortex, what's the right filter size? Well, in theory, the idea would be to use a different filter on those two different things, but that's going to completely mess up the assumptions that we underlie our statistics. So you have to apply a single filter to the whole brain, and there's probably not a single filter that is optimal for each study. So what we normally do is apply a heuristic instead. That is to say, we normally say that the optimal filter size is typically about twice the size of your voxels, right? So if you have 3 by 3 by 3 millimeter voxels, then about a 6 millimeter full width half maximum smoothing kernel is sensible. People vary a little bit. Sometimes they don't use 6, they use 8, or they use 7 or 5. But as a rule of thumb, it's not a bad one. The thing is that the smoothing that you do is going to have a massive effect on the statistical inference that we do. So that's kind of what I was talking about to begin with respect to Gaussian random fields, and we'll talk about it in much greater detail after reading week. But it does matter a lot. So if you smooth with a much larger kernel, big effects are going to be easier to find. Little effects are going to get smoothed out and you're going to lose them, which is essentially what the match filter theorem is saying, right? If the size of the smoothing matches the size of your activation, that's going to be optimal for increasing the signal to noise ratio. Where it's suboptimal, it's going to decrease your signal to noise ratio, making those things harder to find. Okay, so having talked a lot this week the last 2 weeks really, with respect to pre-processing steps, what I want to hopefully get across today is that each of the images that we collect defines its own space. You can see that in terms of the volumes themselves in a functional run, where each individual space needs to be adjusted using the realignment image registration approach. But you can also see it as functional compared to structural, where they each have their own space, as does the standard template image. And you're going to need to map the functional onto the structural onto the template image in order to combine across individuals. And that's what's important about group analyses. You need to have a standard space that allows you to combine all your data that's unbiased. And the one that we all use at this point is the Montreal Neurological Institute 152 template. I should just add, there are some exceptions to that, right? That's what I would say is the normal template if you're testing normal healthy adults. There are specialized templates for different age group children where the brains are at different points in development. There are specialized templates for different stages of dementia and some of the systematic changes that happen in, say, Alzheimer's versus Huntington's versus Parkinson's disease, where there are specialized templates that are ideal for doing those groups. However, if you're doing normal healthy adults, which is the majority of the imaging that gets reported, then the standard reference template is the MNI 152. And, my warning from earlier, I strongly prefer using linear normalization over nonlinear normalization because I think that trying to get rid of the variability that's intrinsic in the fact that our brains are not the same is an error. However, that's a minority opinion. Definitely the rest of the field seems to be perfectly happy with nonlinear registration. So it's not wrong to do it. And it's certainly not wrong to do it even in my class. I just want you to be aware of the consequences of what you're doing so that it's a conscious decision and you're doing what you think is the right thing to do. And then finally, the final pre-processing step is smoothing our data, and we use it to increase the signal to noise and to improve the generalizability of the anatomy when we combine people in that standard reference space.